that in terms that the public can understand. How do we?
Okay.
You cut off a little bit, but did you get those question, Mike?
Yeah, this is Mike Ahern. I'll take that question. I think I understood it before you got cut off. The gases that come out you don't generally see when we take pictures because most of the pictures we take are white light. Sometimes we take pictures in the that are sensitive only to the gas of a particular molecule, but usually they're white light. And we see the jets because sunlight is reflecting off the tiny particles of dust and ice that are being carried up by the jet of gas. If a jet is being produced on the dark side, we in fact don't quite see the base of the jet. We only see the jet when it gets up above the edge of the nucleus so that the sun is above the horizon.
Next question is from Kelly from Sky and Telescope.
Yeah, thanks. Thanks very much. This is for Jessica, I think. Comet Halley, when was visited back in the 1980s, its particles were largely dominated by organic material, I think, and I'm wondering if you're seeing anything comparable, or is this really a comet of a very different composition?
Well, the organics are a little harder for us to get at. I think I showed some evidence that we're seeing sort of a bulk organic peak at this point, and we've, quite frankly, not had enough time to look at it to really tell you too much about its organics. So I hate to not answer the question, but we really don't know yet. And I have to confess I don't know as much about Halley as certainly Mike does. Is there something more obvious there?
No, it's clear that we have organics. Right. It'll take a lot of work to estimate either what kind of organics they are or how many molecules we're getting, whether they're very abundant compared to the water ice grains or compared to the dust grains that are also there, the refractory dust.
Next call is from Mike Wall from Space.com. Go ahead, Mike.
Oh, yeah, hi. This question's probably for Tim, I guess. I just wonder, you actually talked about it just a little bit, but do you know any more about the ultimate fate of the spacecraft? Like what's actually going to happen to it now, or is that still being decided?
Mike, we're going to get Jim Green a microphone, and he will be the appropriate person that can answer that.
Yes, this is Jim Green. We have went out to the community with a request for information and interest in potentially a follow-on activity with this particular spacecraft, and that has closed. We've received that input, and we're currently in the process of reviewing that material, so no announcement is to be made at this point. It's just too early.
We have one question that I have here from one of the .coms, and actually they want to hear from each one of you on your personal thoughts with the data that you have thus far. How has it personally changed from what you have done in the past to now and what you hope to probably do in the future? So that's some personal thoughts on what you've really discovered at this point. So we'll start with you, Mike.
Well, we'll go down the table in order, perhaps. For me, it has emphasized how different comets are from one another and how understanding them is a much more complex problem than the rather simplistic approach I like to normally take. And clearly, when you want to understand how things happen, you want the simple overview, but you have to understand the details as well, and things have just gotten much more complex.
Yeah, I guess for me, and some of the listeners will understand this, but I was an amateur astronomer as a kid. So I saw two comets, Comet Merkos and Comet Aaron Rowland. And, who would have thought that we actually get to see a comet close up like we just did? So that's one thing that just looking back in terms of my personal feeling, it was really sort of very internal. In terms of where we're going, I'm really, really curious about where these particles are, how big they are, where they're going. I'm hoping we can actually determine something more about the particles, and I'll be a happy camper then.
From an engineer's viewpoint, I've been working on small bodies missions for about the last 6 years, starting with the first Deep Impact mission and then working on Dawn and then back to this mission. And getting to these small bodies and getting to comets is hugely exciting and satisfying for me. And then just on top of that, the incredible data that we're finding when we fly by these and get up close and are able to really start understanding what these are like, and just understanding that, so far anyway, we've never been to any two comets that are the same. Every time we have new surprises, amazing new things that we find. Those kinds of things I find just very exciting as an engineer to be able to participate in those. And so I look forward to future missions to these kinds of bodies.
Well, I think for me, it's the wonderful chance to see Hartley 2. And, you know, I used to have a favorite comet. It was called Tempel 1. And we have a new favorite comet, Hartley 2. And, well, like a good parent, they both have their strengths and weaknesses. And it's an incredible opportunity to be able to take the same exact instruments, especially the spectrometer, and compare one for one place to the other. And my personal interest lies in the geology and trying to understand the features that we see both in quite detail on Tempel 1, and now with Hartley 2, the amazing difference is that we have the jets there. And so we can ask the question, what of these features are caused by the jets, or which is cause, which is effect? And comparing the two surfaces, I think, is really going to let us understand how these work. And as far as the future, I love flybys, and Jim, this has been a wonderful experience. I wouldn't do it any other way, but I sure as heck like to get a little closer to these guys and actually land on one of these. So, and that's going to happen soon with Rosette.
I'd rather hit one.
Well, that too. We could do both, Pete. We'll talk offline, right?
Okay.
Okay, thank you all. Let's go back to the phone to Kelly Beatty, again from Sky and Telescope. Go ahead, Kelly.
Thanks very much. I guess I want to try this spectra question from a different angle. Mike and Jessica, can you give us a sense of what kinds of other observations were done at the same time during this flyby that might help you constrain the spectroscopic nature of what's coming off the comet, Spitzer, ground-based observatories, and so forth?
This is Mike Kelly. There were a lot of ground-based observations. For example, both Keck telescopes were being used, and they were being used with high-resolution spectrographs. IRTF was being used, and all these instruments have much higher spectral resolution, so they can more easily separate out the different kinds of organics that are present. Our spectrometer, where we're trying to cover 1 to 5 microns all at once, you can't get high resolution everywhere on a finite number of pixels. So I think the key to unraveling it will be the observations from a wide variety of telescopes like the 2 Kecks and the IRTF, but also including the European facilities and various telescopes in space. Space Telescope was making UV measurements to measure carbon monoxide, for example, and the VLT was being used, and I don't know the details of all the other ones. We have measurements from the Odin satellite of water vapor. I can't give you a complete list.
Jessica, did you want to add something?
No, Mike knows more than I do for sure on that topic. So.
Okay. Now we'll go to Ken Kramer from Spaceflight Now. Ken?
Hi, thank you. Congratulations again on a fantastic mission. 2 quick questions. First, for Mike, I wonder if you could compare the relative amount of water and carbon dioxide in all the comets that we have investigated, the 5 so far. And a question for everyone, did you expect to see these particles? And I wonder if the cameras were retargeted to try to catch those pictures. Thanks.
I think this comet probably has more CO2, more dry ice than any one that's been measured. However, much of the information I have on the other measurements is unpublished measurements by our Japanese colleagues using the Akari spacecraft, so I'd rather not talk about that in any detail because they haven't published their results yet. We did not expect these particles. As I said at the beginning, the fact that we had this experience in Tempel 1 of excavating material and not seeing the particles led us to not really be thinking about them when we got to this comet, even though theoreticians have drawn lots of cartoons showing this kind of phenomenon. They were completely out of our point of view because of the experience at Comet Tempel 1.
And we'll go to the call from Emily Locke-Dawala from Planetary Society. Emily?
Hi, this one's for Jessica. I know that I think that there were some albedo variations, or maybe even some color variations on the surface. I'm wondering if you're seeing that in your data, if you've gotten anything from your spectroscopy on the composition of the surface yet.
There are albedo variations. You can see them in the initial images we released, but we have not yet had a chance to look at the surface in any detail. It's a much more complicated problem than the coma because of the background. It's physically complicated, and it's a little more complicated for our instrument. And we've been focused on this ice story, to be perfectly honest, and that's next for sure. So again, I have to say stay tuned. Sorry about that.
Okay, I think that's going to do it for the questions. I have a couple of comments. First of all, on September 10th, there was an incredible symposium, Comet Discoveries and Encounters, held at the museum here in Washington, where some of the folks here on the stage participated in. I'd like to tell our television audience that you can go to the NASA YouTube site and also solarsystem.nasa.gov, and you can take a comparison from September 10th that was said about comets to now, and you can go in a little deeper, more context. And actually, I was wrapping this up, but now we have another question. Someone said, no, I want to talk. So, can we have the name again, please? Phil Play, go ahead, from Astronomer. Go ahead, Phil.
For any of the three who can answer this, I may have missed it, but the comet is a peanut shape with two lobes and a smooth core connecting them. And you say water vapor is coming from the connector while more carbon dioxide is coming from the lobes. Why would that be? What is it about the structure of the comet that we're seeing that differentiation of the material ejected?
Well, I don't think we know yet. There's a couple of big picture ideas. One is that material is being redistributed over the comet. So you have dust, and in particular, coming out with the CO2, it gets redeposited in the low and gravity low in the middle. That creates a smooth dust covering. Now, that's going to affect how the sunlight is able to reach the bottom, the interior of, not the bottom, but the interior of the nucleus. And so it's possible that that middle either just doesn't have any CO2 and it has been used up, or it never did. Or it's also possible that the dust coating is preventing the sunlight from reaching the CO2 that's actually in the middle. So if we did another impact experiment, we could tell the difference. Told you I'd get back to it, Pete.
Okay, what I'm going to do here is I'm going to pause a little bit because we have reporters joining, and we may get some latecomers again. But before we do that, I want to turn it over to Jim Green. I think you have some comments, sir. Go ahead.
Yeah, I just have a question I'd like to know. And now that you're seeing the material leaving and perhaps can get an estimate of its mass, perhaps you can tell us, is this comet sublimating and expelling gas faster than the others? And perhaps, what's its future life? Is it in the last stages of its life? Will we see it again in 6 years when it comes around, or what?
Okay, I will attempt to answer that, some parts of it. It is certainly producing more total water vapor per second than Comet Tempel 1, even though Comet Tempel 1 is much bigger. It's roughly 300 tons per second. I think that roughly at least half and maybe 2/3 of that is coming from the chunks of ice that come out and then gradually sublime, and only something like 1/3 of it is coming directly from the nucleus, probably mostly near the waist. And that says it's a very active comet for its size. If you try to integrate how much mass is lost as it goes through perihelion, the comet should be losing, on average over the entire surface, something like a meter of surface material every perihelion passage. So at the waist, there's maybe 100 perihelion passages left. So it'll be gone in that length of time.
Jim, did you have a follow-up?
No, it just sounds like in 6 years when it comes around, we'll be able to see it again.
Yeah.